everybody. It's nice to see some new faces around, and thank you all for coming out this evening. I'm Sharon. I'm one of the organisers of the Cafe Scientific team, and in the front row we have the two Emilys. We have Naomi and Becca, who are the rest of the team. A couple of things just to begin with. If you've never been here before and you need to visit downstairs, the little girls' or boys' room, it's down the bottom of the stairs and at the far end of the corridor. The format of the evening is going to be that we'll have a half hour or so talk, and then we'll have a bit of a break so that you can recharge your glasses and think of some questions that you want to ask and some discussion that you want to bring up. Along the lines of questions and discussions, one of our main rules here is that there's no such thing as a silly question. Okay? No matter how silly you think it is, sorry Jen, we've had some fascinating conversations and discussions that have been based on things that people think are silly questions. There is no such thing, so please feel free to take part in the discussion in the second half of the evening, because that's what this is all about. You're not here just to sit and listen, you're here to learn and you're here to take part in the whole discussion of things. Apart from that, as you can tell, it's quite a small venue, and while we are very informal, please just be aware that sound does travel, so if you're having a chat to the person next to you, please try and do it quietly, or listen to Jen instead. It's without further ado that I'd like to introduce our speaker for this evening, who is Dr. Jenn Gupta, who's from Portsmouth University. She's come all the way over to speak to us, and she's going to give us a fascinating insight into nature's death ray bands. Everybody duck. Thank you.
Good evening everyone. As Sharon said, my name is Dr. Jenn Gupta and I work at the Institute of Cosmology and Gravitation at the University of Portsmouth. So here's the rather lovely building that I work in. It's a rather swanky new building down near the seafront. The Institute of Cosmology and Gravitation, there's about 50 of us in the department. It's a research department made up of academic members of staff, so your professors, your lecturers, research staff and PhD students. And the research that's done there is sort of on the bigger scale of things. So we sort of work from galaxies upwards, looking at galaxy evolution, alternative theories of gravity, the beginnings of the universe. Some of our researchers study like microseconds after the Big Bang. A lot of it is quite theoretical stuff, because we're in our offshoot of the maths department. Although we do some observational stuff, and actually on my drive down here I switched over to Radio Sloan and randomly heard one of our researchers talking about supernovae, which was a bit strange. Before I was here, so I've worked here for about 2 years now, I worked at this place. This is the Jodrell Bank Observatory. This is the Lovell Radio Telescope. I don't know if anyone's been there. It's the third largest fully steerable radio telescope in the world. There's some bigger, but they're just like dishes in the ground. It's 76 metres across. It's pretty huge. It's been there since the 1950s, doing radio observations of galaxies and of the universe. So while I was there, I wrote this book called Multi-Wavelength Studies of Radio-Loud Active Galactic Nuclei in the Fermi Era, which is a really grand-sounding title that encompasses a lot of little different things that I managed to do. And then after 4 years of doing that research, I got to dress in really silly robes. They look a little bit like a cream egg wrapper. I just like showing that. It just looks ridiculous. They make you wear really stupid robes. And I got my PhD. So tonight I just want to talk a little bit. I forgot to press start. That's fine. A little bit about my research and what I did. But bear in mind that that was now 2 years ago that I finished that. And my day-to-day job is actually to go out and talk to kids about astronomy and space and the universe and organise public events and stuff. So be nice to me if I forget some things. So we'll start off nice and simple with the night sky. So this is what you might see if you go somewhere really dark and take a look up at the night sky. You have to get really far away from light pollution to get a view like this these days, away from the city. So you see stars, lots of stars, far more than you'll see in Bournemouth or Portsmouth. And you also see this band of light going across the sky, which is our Milky Way galaxy. So this is us looking through to the centre of our Milky Way. If you go somewhere really dark, you get even better sights of it. And I had to show this because this does look like a death ray pointing to space. So this is the Very Large Telescope up in Chile. We're not very good at naming telescopes. What they're doing here is they're shining a laser up into space to use as an artificial star. So you shine this light up, you shine a laser up, you take a picture of it with your telescope, and that tells you the effects that the atmosphere is having on your stars, because that light, the laser pointer, as you can see, is a point source. So if it doesn't look like a dot, then you know what the atmosphere is doing to it, and you can correct all your images. That's not really that important. I just really wanted to show a picture of a laser being shot into space. And also, this is what you see in this. If you go down to the southern hemisphere, you really see the Milky Way in the centre of our galaxy. So I'm showing you these pictures of the Milky Way, but you might want to know what our galaxy really looks like. And this is an artist's impression of what we think our galaxy looks like. So the Milky Way is a spiral galaxy, we believe. It's made up of maybe 200 billion stars, all held together by gravity. You've got a central bulge in the middle. That's orange because there's older stars in there. And the older stars are cooler, so it's opposite to what you think with your taps. Colder is actually red, and hotter is blue. So in the stars, in the spiral arms, you've got your younger stars where the stars are forming and they're glowing a lot hotter. They're burning hotter than the older stars that are kind of burning out in the centre. And that might seem a bit weird to you, but it's, if you've ever used a Bunsen burner, you close it up and it goes hotter and the flame goes blue. If you've ever put a piece of metal into a fire and heats it up, it first glows red and then it glows white, which is the blue-white colour. In case you're wondering, we're about here. So we're about 2/3 of the way out from the centre in something called the Orion Spur. No one really knows how many spiral arms the Milky Way has, which is kind of funny. Because if you think about it, we're inside this galaxy, so it's actually quite hard for us to figure out what it looks like outside. We come up with these artist impressions, but there's a lot of arguments going on at the moment about whether it's 2 arms or 4 arms. I don't know, so we'll move on. So we see lots of galaxies out there if we point our telescopes up at the night sky. This is the Andromeda galaxy. This is the closest spiral galaxy to us. You might recognise this picture because Apple used this as their default background for years, but they took out this galaxy for some reason. They didn't like that, so they just took it away. So Andromeda is the nearest spiral galaxy to us, the nearest major galaxy to us. It's a spiral galaxy like the Milky Way. It's a bit bigger, I think, that has less stars, or the other way around, I can't remember. But that's what our galaxy would look like if you could actually go out and have a look back at our galaxy, which you can't do because we haven't got good enough rockets yet. So we see spiral galaxies like this, our spiral galaxies with our sort of orangey bulge in the centre and our blue spiral arms coming out. There's one other major type of galaxy, which are the elliptical galaxies, which just look like blobs of stars. And as you can see, this one looks kind of orange. So the elliptical galaxies tend to be made up of much older stars. There's not really any star formation going on. You're not seeing that blue light from the younger stars. So these are often called red and dead. Just collections of so many stars that you can't even see the individual stars in them. They just look like these fuzzy blobs. So we see a lot of galaxies out there. This is the Hubble Deep Field image. It's a very famous picture. What scientists did was they pointed the Hubble Space Telescope at what looked like an empty patch of sky, and they took observations for days, and eventually they collected enough light from all these distant galaxies that this picture has about 1,500 galaxies in it. It's tiny. I can't remember. It's something like, if I worked it out once, it's something like holding a Lego brick at the other end of a train carriage. That's about the size of this patch of patch of area in the sky, and it doesn't look like it has anything. You didn't know until the Hubble Space Telescope came along that there was anything there, and it found all these galaxies. Later versions of the Hubble Deep Field have got thousands, tens of thousands of galaxies in them, and there's a lot of galaxies out there. So I don't know if anyone's heard of a project called Galaxy Zoo. This is a citizen science project online at galaxyzoo.org. Basically, there's too many pictures of galaxies for us to look at. One project that we're involved with at Portsmouth is called the Sloan Digital Sky Survey. So There's a telescope in New Mexico that's taken pictures of a quarter to a third of the sky, and it's taken photographs of over 1 million galaxies. And so astronomers want to know what all of these galaxies look like, but we can't sit there and classify them all. We can't say whether it's a spiral or an elliptical. And one PhD student tried to do this. He classified 50,000 galaxies in a week and then said never again. So decided that we should try and get members of the public to do it. Because this is something that computers can't do. Computers are really bad at shape recognition. Facial recognition software just isn't very good. It's a similar thing that we've been trying to do with the galaxies. But humans are very good at pattern recognition. So we put all our galaxies up online. So if you want to go and help some of the researchers at Portsmouth with their research, you can go to galaxyzoo.org after this talk, and you can help us out. There's about 1 million people signed up to the Zooniverse. There's a whole load of other projects now, not just Galaxy Zoo. We've got something like the 6th largest army in the world, if you consider us to be an army, which is quite cool. And this is doing real science. The whole point behind Galaxy Zoo is that there are real scientific questions that we want to answer, and something like 40 scientific papers have been written using people's classifications. Now I've got my Portsmouth plug out of the way, I can talk about my stuff. So, nature's death ray guns, yes. So some galaxies out there, when you look at them really closely, they don't just look like these fuzzy blobs. You might not be able to see it, but here, on this elliptical galaxy, there's something that's just coming out from the centre there, something that looks a little bit odd. And so what you can do is you can look at these galaxies with different types of light. You don't have to be restricted to the visible light that our eyes can see. We can use telescopes that are sensitive to all different parts of the electromagnetic spectrum. So what we see as light is a wave, and if you stretch out that wave and you get longer and longer wavelengths, you go down beyond the red, down to the infrared, then microwave, and finally radio. If you go up the other way, you squish them down from the purple, you get to ultraviolet, X-ray, and gamma ray. And so these are all different types of light, and we can build telescopes that are sensitive to different parts, and we can really probe the universe using much more than just this visible light that we see. So we can use radio telescopes like that Lovell telescope that I showed at the beginning, the one at Jodrell Bank. And when we point our radio telescopes at that galaxy that I showed you just now, you see something like this. So you see this giant structure in the radio. You see a really bright bit in the centre, and then you see something shooting out from the middle, just like in the visible light you saw a little bit, a hint of something shooting out from the centre. It's a lot more obvious in the radio. And then on the other side you've got a load of wiffly stuff. And that is actually the technical term that we use. We call this all wiffly stuff. So you can point your radio telescopes out across the sky, and we don't have to wait till night. Radio telescopes can observe 24 hours a day. They can observe through the cloud, which is why you can still have a radio telescope in Cheshire. And you find a lot of these objects. So this is one of my favourites. This is an object called 3C273. And again, you've got this really bright bit up here, and you've got something shooting out from the centre. But if you go back to the optical, and you point an optical telescope, a visible light telescope, at the point in the sky where this object is, you don't see a galaxy, you see a star. So this picture now here is centered on that same position, and this star here is what you see. You don't see a galaxy. So it took astronomers quite a while to figure out what on earth was going on with these objects. It turns out that this is actually also a galaxy here. It's just really, really far away. And so there's a galaxy here, and we call these galaxies active galaxies. And I have to show you this next thing because it took me ages to make, but it's really lame. I don't mean when you say active galaxies, it's not galaxies working out. It's galaxies that are giving off far more energy than you can account for by if you added up all the energy that comes from all the stars. So we can just about work out how many stars are in a galaxy. There tend to be maybe 100 billion, 200 billion stars in a galaxy. And if you assume that they are all an average star, you can work out how much energy you should be getting from that galaxy, how much light you should be getting. And when you look at these active galaxies, there's far more. They're orders of magnitude. They're tens, hundreds times brighter than they should be from the stars. So we realise that there has to be something going on that makes them much more energetic. And this is a cartoon of what we think it is. So it's all to do with the supermassive black hole in the centre. So every galaxy has a supermassive black hole in the middle of a galaxy. At least we think every galaxy does. When we say supermassive black hole, we mean a black hole that's maybe 1 million or 1 billion times the mass of our sun. Concentrated, mass concentrated down, squished down as much as it can until no light can escape. And so in a lot of galaxies, this black hole is just sitting there. It doesn't really do much. You don't really know it's there. But in some galaxies, our active galaxies, it's kind of a monster. You've got a black hole in the center and then an accretion disk around it. So this is just a disk of dust and gas that's swirling around the black hole. And as it swirls around, it's falling into the black hole. And the black hole's basically eating all this stuff up. And as it rotates around, it heats up because of friction. So just like you rub your hands together and your hands warm up, this accretion disk warms up. But it doesn't warm up, to like 20 degrees. It warms up to thousands and thousands of degrees. So instead of emitting infrared light, which is basically what you emit when you rub your hands together, it's emitting X-rays. So you've got a lot of X-rays coming from the center, coming from this accretion disk. What else have we got? What we've got that I'm really interested in are the jets. So these are those bits that you see in the radio shooting out from the center. These two jets coming out here. And as you can see, this system is asymmetric. So the angle that you look at an active galaxy will affect what you see. Because if you look at it how we're looking at it, and imagine it's not cut out here, the accretion disk is completely obscured. So you wouldn't actually see those X-rays. And you see those jets coming out of the center. If you flip it up so the jets are pointing towards you, then you see the X-rays as well. And the Blazars, the nature's death ray guns, are the ones where the jets are pointing directly at us. Now these jets are made up of charged particles like electrons traveling close to the speed of light. So they're traveling ridiculously fast, and as they travel, they give off these radio waves. It's a bit like having the LHC, the Large Hadron Collider in space. You basically got a massive particle accelerator accelerating electrons up to near the speed of light out in space, which is why they got called nature's death ray guns in one popular article, as you do. So let's go on to talk about understanding nature's death ray guns, or a little bit about it anyway, because we don't really understand a lot about these objects. So nature's death ray guns, or Blazars, not Blazars, a lot of jokes about that through the PhD. How do we understand them? Well, we look at them with our different telescopes. So we use the different kinds of electromagnetic radiation to take a look at them. And so we'll go back to our electromagnetic spectrum, and we'll go right down to the radio side of things. So the longest wavelengths. Now, in order to get a high resolution picture, get radio wavelengths, you need a really big telescope. So the resolution, just like the resolution of a camera, the bigger a camera is, the bigger your lens is, the better resolution you get. It's the same for this, and the longer your wavelength, the even bigger you need it to be. So you need giant radio telescopes, which is why you've got the Lovell telescope, which is 76 meters across. It needs to be that big to collect up those radio waves, and even then it's not as good resolution as the optical cameras. So what we do instead is we build lots of smaller dishes, and we point them all at the same thing. And then we use computers to combine those signals. I mean, as if you had a giant radio telescope that was as big as the furthest distance between those two telescopes. So this is the Very Large Array in New Mexico. You might recognize it from Contact. Haven't found aliens with it yet, but we are looking, genuinely, just not sitting there with our headphones over our heads. So the biggest distance you can have between these dishes is something like 27 kilometers. So you've suddenly got, instead of a 76 meter telescope, you've got the 27 kilometer telescope. And then you can really start getting into a lot of detail in the radio. You can get resolutions that are comparable to the Hubble Space Telescope. Unfortunately for me, Blazars look really boring in the radio. So instead of getting those nice pretty pictures, what we get are lots of dots. So we get lots of really bright dots. Which is kind of boring to look at for a few years, but also really interesting, because what happens when you've got the radio jet pointing towards you is something called Doppler boosting. So because these electrons are traveling close to the speed of light and then they're coming towards you, you can see things like it looks like the jets are travelling faster than the speed of light, which is kind of cool. And you see them being really bright. They're brighter than they should be. Their emission is boosted up compared to what it should be if it was going side on. So we find a lot of these blazars in the radio, and we see them as point sources, which is kind of cool. But what's really interesting actually is when you look at the other end of the spectrum. So you go all the way up to gamma rays. And now this is really far away from radio. Right? There's this complete other end of the spectrum. But you actually find that these blazars, where you found a radio one, you'll often find a gamma ray one. So there's some link somehow between the emission process that's giving off the radio and giving off the gamma ray. Now to look at these in gamma rays, you can't do it from the ground, because luckily the atmosphere blocks gamma rays from coming down, otherwise we'd fry. So this picture just shows you where you can, with the electromagnetic spectrum, where you can view from the ground. So here's your radio window. You can do all your radio astronomy from the ground. You then have to go up into space for the infrared, back down again for a bit of visible, and gamma rays, X-rays and ultraviolet are all mostly blocked by the atmosphere. So we put our gamma ray telescopes into space. I kind of think gamma ray telescopes are kind of cool. I'm not a gamma ray expert, I'm more of a radio astronomer, but I've used data from this telescope. So this is called the Fermi Gamma Ray Space Telescope. This is an artist's impression, it's not a real photograph, but gamma ray telescopes are a lot different to normal telescopes. Normal radio telescopes, amateur optical telescopes, they'll work by focusing the light to a point. So an amateur telescope that you might have looked through will either have lenses or mirrors in it that will bend the light and focus it to a point, focus it to where your eye is looking through. The radio telescopes do the exact same thing. They're a big dish that the radio waves come down and they bounce off to a receiver at the top, or they bounce a few times to a receiver at the bottom. But gamma ray telescopes can't work like that because gamma rays are far too energetic. If you tried to have a mirror or a lens to bend gamma rays, they just wouldn't bend them enough ever to focus them to a point. So instead, what the Fermi Gamma Ray Space Telescope is a bit more like a detector at a particle accelerator. So your gamma rays hit the telescope, and that causes a cascade of particles. So that gamma ray turns into maybe an electron and a positron, and then they decay into other particles, and eventually you pick up the energy at a point, and you have to sort of trace it back through the detector to find out where it came from and what energy it had, which I think is kind of neat. Now, because of this, our gamma ray telescopes don't have very high resolution. So while we've detected active galaxies, blazars in the radio, sort of in the thousands, until recently we knew of 66 blazars that are being detected at gamma rays. And this telescope really revolutionised this. This was launched in 2008. And this is a 2-year map of the gamma ray sky. So it might look a bit weird to you, that's an all-sky map. So it's basically exactly the same as taking a globe and unfurling it to be a map of the world. When we're observing the entire sky, we're just looking on the inside of that globe. And so you unfold it and you decide your projection, you get an image like this. So here, the yellow is the brightest, yellow and white are the brightest bits in gamma rays, and then red, and then finally blue and black. So this running across here is our Milky Way. This is all the gamma rays coming from our Milky Way. Now the Milky Way doesn't give off that many gamma rays, it's just that it's really close to us. It's the same as actually the sun is the brightest radio source in the sky. The sun doesn't give off that many radio waves, it's just really close to us. But all of these dots out here, all these little dots, nearly all of them are blazars. And Fermi's detected, it's confirmed about 800 blazars in the gamma ray, and it's got unconfirmed a few more hundred than that, which is kind of neat. And so you can put this map, I don't do it, but you can put this map next to a radio map, and you can point out that source is that source, and that source is that source, and that source is that source. So you've got to, what you want to know is how these gamma rays are produced. At least that's what I wanted to know during my PhD. So all of you now want to know how the gamma rays are produced.
Tell us.
Tell us, we don't know, is the simple answer. But We figure it must be to do with this jet, because when you see a correlation, what you see is that if a blazar is bright in radio, it will tend to be bright in gamma ray, and then the one that's less bright in radio will be less bright in gamma ray. So you figure that there must be some kind of connection between the emission processes. Now, I've said it a couple of times, but I've not really explained it, but the radio waves that are coming out from the poles are due to something called synchrotron radiation. It's a really bad cartoon that I got off the internet. Basically, if you have a magnetic field, and this happens on Earth as well, this isn't just in space. You have a magnetic field and you have an electron near to it, that electron will spiral round. It will go round and round and round, spiral around the magnetic field. And as it does it, it gives off radio waves. So these radio waves are what we're seeing. We think that the jets are to do with magnetic fields somehow getting all twisted up and collimated into the jets, and then these electrons that are sort of left over from the black hole eating everything up can spiral around and give off these radio waves. And then the emission process that we think is causing the gamma rays is something called inverse Compton scattering, which is basically when you have an electron meeting a photon. So a photon is just a particle of light, or radio wave. You have an electron hitting that. What will happen is the radio photon, or the visible light photon, will take the energy from the electron. And if a photon gains energy, what it does is it moves up in the electromagnetic spectrum. So a radio one could move up to a microwave one can move up to a visible one can move up to ultraviolet, etc., etc. So if you have enough energy in these electrons, and these electrons in the jet have a lot of energy, then they can give that energy to the photons, and these photons can be boosted up to gamma ray energies. So you might be sitting there thinking, well, that's great, but where are these photons coming from? Which is certainly what I sat there and thought. So the bits that I missed out on my cartoon are these ones, the broad line region and the narrow line region. And so these are basically clouds of gas that are moving around because of the black hole. And as this gas is moving around, it's giving off photons, it's giving off light. And so if you have an AGN with a broad line region and a narrow line region, you can have your photons of light there that will then get boosted up by your jet. There's also photons coming from the accretion disk. I said it gives off X-rays. The X-rays just photons, particles of X-rays. And you've also got them coming off the jet itself. Those radio waves are made up of photons. So you've got a lot of different options for where your photons are coming from for your inverse Compton scattering, and you've got to try and work out where they're coming, which one of these is responsible for it. Now there are some clues. I'm not going to give you the answer because I don't know, but there are some clues. This is a great thing about research. So we can look at the optical spectrum of an AGN. So this is basically taking the light, the visible light now, from that galaxy and putting it through a prism to make a rainbow. That's basically all this is, but it just doesn't look as pretty. So when you do that, different elements will give off different specific colours. Even if you don't know that, you do know that because you are probably, I would assume, have all seen fireworks. And so the different colours from the fireworks are because there's different elements within those fireworks. And so if you have hydrogen, for example, you have whatever colour this is, which I don't actually know. Let's say it's blue. So if you have, close enough, it's not, and you're videoing this, so someone's going to stop me after that. But if you have hydrogen, you'll get a very specific colour, very specific, and you have your rainbow, you have a very bright bit at one colour, a very bright bit at another colour, a very bright bit at another colour. You can identify that as hydrogen. And instead of just putting them as a colour, what we do is we make them a graph of how bright it is at different colours. And that's what you got there. So this is telling you that there are lots and lots of visible photons that can be accelerated up to gamma rays in some of these objects. This is 3C273, that one I showed you before. So that's great, you've got your source of your photons. But some of them cause a little bit of a problem and don't have any bumps. So this is one of my objects in my sample that I looked at for my PhD. Nothing in there. Completely featureless, very boring. But that means that this is indicating that this this galaxy doesn't have any sources, external sources of photons, so it doesn't have that broad line region, it doesn't have that narrow line region. And so the only way that you can get the gamma ray emission in this galaxy is if it's those jet photons, those radio photons from the jet that are being boosted up. So that's basically as far as I got with all of this in my PhD, and then a lot of people argued with me, and then I gave up. And then sometimes your galaxy doesn't show any evidence of being active, which is really weird because you know it's an active galaxy because you're seeing it in the radio, but when you look at the optical it just looks really boring. Never came to the conclusion of why that was. I'm still working on it. But I will finish by having, I like to think about what would happen if one of these was pointed towards us. What would happen if a jet was pointing directly towards us? So this is a picture of what's called the Death Star galaxy, 3C321 I think it is actually. But this is a system of two galaxies here, and this galaxy is an active galaxy. It's firing a jet off in this direction, and this little galaxy happened to get in the way, and has sort of been fried. You can see this is showing you the different colours are showing you the different types of radiation. So this is the radio wave coming out. You've got ultraviolet in there. I think it's orange. Yellow is the optical picture. And so this galaxy, this poor galaxy, has got in the way of the active galaxy, and the jet has sort of fired through it and destroyed a lot of it. This galaxy is about 20,000 light years from this galaxy. The Earth is about 20,000 light years from the Milky Way's black hole, Milky Way centre. So this could be us here being fried by a jet, which isn't. I mean, it would destroy us. You know, you have the gamma rays blasting at us would just destroy the atmosphere, and then we'd all die. But it's okay because. For two reasons. The first one is that our Milky Way's black hole isn't active, so that's a good thing. We are not living in an active galaxy. We know there's a black hole there because of this movie. So this movie shows us the motion of the innermost stars in our galaxy, the stars closest to the centre of our galaxy. And what astronomers did was they took photos, over a long period of time and put them together to see the motion of the stars in the centre. And what you see, and we may have to play that again. Is that going to play again? Play again. What you see is that they are avoiding an area in the centre, and they're being kind of whipped around it. And so that suggests to you that A, there's something there, and B, it's got a lot of gravity, it's got a lot of mass, and its gravity is affecting them, the stars in this way. So you kind of see that they're shooting around over here. And you can weigh the black hole in the centre of the Milky Way, and it's only about 4 million solar masses, 4 million times the mass of the Sun. In our active galaxies, we're talking about billions of times the mass of the Sun, so it's a pretty puny one in the Milky Way. The other reason not to worry about an AGN switching on or anything in our Milky Way is because we're here in one of these spiral arms. Blazars aren't really found in spiral galaxies. They tend to be found in the elliptical galaxies. And even if you did have an AGN an active galaxy in this galaxy, the chances are that the jets would shoot out from the centre, so they'd be coming sort of directly towards you there rather than shooting through the spiral arms. And so I don't reckon that even if there was a jet there, I don't reckon we'd even know about it. We wouldn't really be affected by it at all. But just for fun, there's something else that's going to happen to us in about 4 billion years' time, which is that our own Milky Way galaxy is on a collision course with the Andromeda galaxy. So the Andromeda galaxy, that spiral galaxy that I showed towards the beginning of the talk, is coming towards us. Gravity is pulling these two galaxies together, and as far as we can tell, they are on a collision course and will collide in about 4 billion years' time. So we can watch a movie of that. So they'll come towards each other, and what happens is they won't just kind of plonk together, they sort of pass through each other, and you see these beautiful structures. The stars all get gravity, all affect it all, and they swirl around, and they'll do a couple of passes probably. And then eventually these two spiral galaxies will merge together into one of those elliptical galaxies. And so we find these blazars in elliptical galaxies. So one thing we don't know is whether this sort of process will then switch on the active galaxy in the centre. Maybe it's this process of two galaxies colliding, their black holes merging together, that triggers this active galaxy and these jets to come out. So maybe in a few billion years' time, the Milky Way will be an active galaxy. During this process, the sun may get flung out into space and be a rogue star with the planets floating around, going around it. It may become part of the Andromeda galaxy for a little bit. So as they do those passes through, the sun might get attached to the other galaxy for a little bit and then come in. It's very unlikely that any stars will hit any other stars. It's a bit like standing at two ends of a football pitch and throwing a handful of sand at each other. You know, the actual sand grains don't hit each other. There's a lot of space in between the stars. But it will look very pretty, so some people from NASA did some Photoshop to see what it would look like as Andromeda came towards us.
Friday afternoon job.
Yeah, so this is the Milky Way, and here's Andromeda coming towards us. We don't really need to worry, because at about the same time the sun is going to come to the end of its life, and it's going to swell up into a red giant star and engulf us. So one of these, I don't know which one's going to happen first, but we won't be around to see it. And on that happy note, I think we'll stop there. Taking a few questions.
On that happy note, I'm not sure whether or not Bosca Nova will still be in existence at that point in time either, so I think we're okay just now. As I said, feel free to now charge up your glasses. We'll have a 10-minute break or so, and then think of some questions, and we'll get back to the real part of the discussion once you've got something else to drink. Thank you.